In this presentation, we're going to have a look at how DNP3 messages are constructed. We will be breaking out requests, but we won't be covering responses due to their complexity. This is an example of a DNP3 request and a DNP3 response. The upper message is a DNP3 request, the lower message is a DNP3 response. DNP3 uses the application, the transport, the data link, and physical layers of the OSI 7-layer stack. Looking at the colors, red is the application layer, green is the transport layer, blue is the data link layer, and black is all the packets that are sent through the physical layer. Let us take a closer look at the layers and how they are implemented for DNP3. I will be using the transport of a package via FedEx as an analogy for each layer. The physical layer moves the data. The physical layer for DNP3 is always byte asynchronous, 8 data bits, 1 start and 1 stop bit with no parity. There are many communication media available for transmission: RS-232, RS-45, digital cellular, radio, dial-up, satellite, LAN or WAN. Many mediums can be used for DNP3. Let us now take a closer look at the data link layer. This message example is a valid DNP3 request. This is the data link header of that request. Let's have a closer look at the data link header and see what it means. So the data link header is this part of the message right here. The data link layer handles DNP3 message delivery. All DNP3 messages have a data link header. The data link headers are all 10 bytes in length. So where do we start? The data link header in DNP3 always starts with 0564. These are the first 2 bytes. This signals the start of a DNP3 message. As an example, all FedEx boxes have the same FedEx logo. This is like the brand name. How big? The next byte in the header is the length byte. This is the length of the request message. The length calculation does not include the length byte itself or any CRCs in the message. Maximum length is 255 bytes. Longer messages are possible, but this is handled by the transport layer. Comparing this again to FedEx, this is like a weigh bill. When you ship an item, you need to enter the weight and size of the package. What do you want to do? The next byte in the data link layer is the control byte. This determines how the message is to be delivered and handled by the receiving end. For example, confirmed and unconfirmed are like insuring or uninsuring a package when you are preparing to send it. Looking at the FedEx example again, the weigh bill determines what type of delivery service you would like. Is it regular, express, insured, uninsured, etc.? Where is the package going? These are the next 2 bytes of the destination address. Valid ranges are from 0 to 65,520. In the FedEx example, the weigh bill shows the address the package is to be delivered to. Where is it from? The next 2 bytes contain the address of the source of the message where it is being delivered from. Valid addresses again are from 0 to 65,520. In the FedEx example, the weigh bill shows the address the package is to be delivered from. And finally, the last 2 bytes of the data link header are the air control, which is the CRC. FedEx has many air control functions in place, such as signing for packages, internet tracking, etc. So in summary, the data link is FedEx for DNP3 message delivery. We can see a comparison or an analogy between DNP3 and FedEx as we move from preparing a package to be shipped to it being delivered. Let's have a closer look now at the control byte, which is kind of like the delivery instructions. Depending on which bits are set in the control byte determines how the message is to be delivered and handled at the receiving end. Each bit has a particular function. As an example here, we can see that the direction bit, if it's set to a 1 or a 0, tells us, is this coming from a master device or a remote device? If bit 2 is set to a 1 or a 0, this tells us, is this a primary message or a secondary message? And so on. We have frame count bit valid, and then we have the primary and secondary function codes. So let's take a closer look at the primary and secondary function codes. The primary and secondary function codes can be broken down into individual bits with different functions. The 8 bits of the data link control can all be summarized in this table. This table allows us to break out whatever the hexadecimal value is from the data link control and break it into its individual components. So in this slide we have our DNP3 message structure. I like to call it our DNP3 breakout sheet. So up top here we can see our data link header. So we've gone through briefly the data link header and looked at all the bytes and what each of these bytes means. So here's our 05, our 64, so this tells us it's a DNP3 message. Here's our length byte. Here's our data link control. So this is our breakout for data link control. So depending on which bits are set, we can determine what is happening with this message. Is it a primary message? Is it a secondary message? Is it from a master? Is it from a remote? Here we have our primary and secondary function codes, and we can use the table down below here to either break out the whole data link message, or if we want to just break out the primary and secondary function codes, we can look in this table. So this is the sheet we're going to use to break out the DNP3 messages. Let's have a look at an example to illustrate how to interpret a DNP3 data link layer header. It's a good idea to have the DNP3 breakout sheet handy in order to do this. So starting off with, we have the first 2 bytes, so 0564, these are called our start octets. So every DNP3 message, whether it's a request or a response, will always start with 0564. The next byte is the length byte. So in this case here, 14 in hexadecimal, if we convert that to decimal, we get 20 bytes of user data. Now, remember, the length does not include 0564. It does not include the length byte itself. It does not include the CRCs. So the CRCs, they're the last 2 bytes on each of the lines here. So there's my CRCs. So if I add it up, so here I have these 4 bytes, and here if I add these up, I have a total of 16. So 4 plus 16 is 20 bytes of user data. So now let's look at the data link control. That's the next byte. So I can see in the hexadecimal it's C4. So this means it's a primary unconfirmed message from the master. So let's just jump ahead and look at breakout. So if we go to the breakout sheet, it might be a little hard to see, but I can see there's my 0564 at the top here. There's my 0564. There's my length. Now here's my data link control. So just like we were looking at in some of the previous slides, this data link control, I can break this into 8 different bits. So if I label this up here, this first 4 bits, that would be my C. This would be my 4. So I could fill in exactly which bits are on here, and I could determine what is happening with this in the data link control with the message. So if I look here and I use this table and I follow down, I can find here C4, very hard to see here, but C4, and if I read this graph now, or I read this table, I should see, I can see that it's primary, it's unconfirmed, so that's this row right here, unconfirmed message, and it's coming from the master because it's in this column here. So this allows me to quickly break out the data link control. So let's have a look now at the next 2 bytes. So the next 2 bytes are the destination address. Now, what's important to realize here when these bytes are all lined up in a row here, what's actually happening is this is actually the least significant bit, and this is the most significant bit. So for both the destination and the source address, this is least significant, this is most significant. So this is just how the bits are lined up as they're being sent down the physical layer. So to interpret this, what we need to do is, once we read this, we need to break it out so that least significant bit we put on the right hand side, most significant bit on the left hand side. So we would read this as 0, 1, this is the least significant bit. So this is in hexadecimal. If I convert it to decimal, that means 1. So that's the address of the destination device. So if I move on to the next 2 bytes of information, so this is the source. So this is where is this message coming from? So in this case, it's if I take the least significant bit up in the message structure here, and I bring it down and I separate it to least significant bit on the right hand side, most significant on the right hand side, 64 in hexadecimal, that converts to 100. So the address of the master station is 100 in decimal. The address of the remote station is 1 in decimal. So what's important to remember here is to flip those 2 bytes from both the destination and the source when you're reading them, to make sure you get the correct address. So again, using the breakout sheet, we can see the start bytes 0564, we can see the length, we can see the data link control, and remember we can just follow this through and we can go to the appropriate table, which this table down here will allow us to break out what this C4 means. Then looking up top here again, we can see here's our address. So remember, in the actual frame here, it has least significant, most significance. But if we want to interpret this, we have to flip these two. So same thing with the source. So least significant, most significant. But if we want to interpret this in decimal form, we need to flip those. So the final 2 bytes here, this is the CRC. So this is basically an example here showing how to break out the data link header and which parts of the breakout sheet you need to use to break this out. So what I'm going to show you right now is a screenshot from ASC 2000, and this is just showing the communication between the RTU and ASC 2000 using the DNP3 protocol. So if we have a look up in the upper left, we see the arrow indicating that this is a request going out. So I see 0564. If I look at the interpretation on the right hand side, this says reset link request, data link header. This just tells all the devices out on the network that this is a DNP3 message that's coming. I see my 05. This is the length byte. So if I look over in the interpreter, it says the length is equal to 5. The next byte we have is our data link control, C0. So the breakout for this is reset link confirm, direction is equal to 1, primary is equal to 1, FCV is equal to 0. So essentially, the data link control is telling us that this is a primary message and it's coming from the master station because the direction bit is set to 1 and the primary bit is set to 1. So this is a request coming from the master station. So the next 2 bytes that we can look at are the destination address, and in this case we have 6F00. So if we convert that to decimal and remember to flip the bytes, we have a destination address of 111, and the next 2 bytes are the source address, which in this case is 6400. So if we flip the bytes and convert that to decimal, that's a source address of 100. Finally, the last 2 bytes, AD73, this is the CRC. So these are the 10 bytes of the data link header, and we can see how they're broken out with ASC 2000, and this is an example of being connected to the RTU in the lab.